Hello everyone, welcome to our presentation. We are a security team from Tencent Security Xuanwu Lab. Today we will be presenting on the topic, reviving JIT vulnerabilities, unleashing the power of Maglev compiler bugs on Chrome browser. My name is Wang Zheng. I'm mainly focused on browser security and kernel security, and my partner specializes in browser security and software security. He is also a Google Chrome bug hunter. First of all, let me introduce our research target, Maglev compiler and related knowledge. There are two typical compilers. One is AOT compiler, also known as static compiler. It translates the entire source code into machine code before running the program. They are commonly used in static languages such as C and C++. It has a low cost on memory. The other one is a JIT compiler, which is mainly suitable for dynamic languages such as Java and JavaScript. It performs real-time optimization by analyzing the information in the running program. Its optimization methods are more diverse, so the quality of the code is high. V8 is the JavaScript compiler in Google Chrome. As shown in the diagram, V8 passes the source code file, turns it into an abstract syntax tree. It produces various bytecodes and uses speculative optimizations to get bytecode. The generated code will be translated into machine code based on the architecture. Turbofan is the optimization compiler of V8. It has a type system. It performs type analysis on the code so the smarter decisions can be made. For example, if the type system can determine that a variable will always be of integer type during its lifetime, Turbofan can avoid generating code that handles floating point numbers, thereby improving execution efficiency. Turbofan generates highly quality code, but the complicated optimization results in slow speed. To address this issue, V8 introduced a non-optimized compiler called Sparkplug. Sparkplug traverses the bytecodes, offloading complex operations to built-ins, and reuse ignition to accelerate compilation. This part will explain why we choose Maglev compiler as our target. First of all, the bug of JIT compiler has high exploitability. In recent years, many in-the-wild bugs in Chrome have been found in the Turbofan compiler. And the Google security team also noticed that and increased its defense investment in Turbofan. Thus, many JIT bugs exploration techniques have been fixed. So, even if the bug exists, it is more difficult to exploit. Over the past year, the Maglev compiler project has seen rapid development progress. By July of this year, the basic development was completed. As shown in the picture on the right, Maglev's number of commits in the past year far exceeded that of Turbofan. Maglev has some similar optimization system like Turbofan, which made it a good target to discover. Let's learn about the design and implementation of the Maglev compiler. Maglev is an optimizing compiler based on SSA. Its design goal is to achieve faster compilation speed than Turbofan and better code quality than Sparkplug. The overall compilation process can be divided into the following stages, which we will introduce one by one. SSA means static single allocation representation. Each variable can only be allocated and defined once before they are be used. As shown in the figure 1, the two branches assign values to y respectively. In order to get the SSA node, we need to create two variables, y1 and y2. In the bottom basic block of figure 2, W2 is not sure about using y1 or y2, so the find node is used to indicate that either y1 or y2 is selected. During the graph building phase, Maglev converts bytecode into SSA nodes and creates fine nodes for loops and exception handlers. Additionally, it splits basic blocks based on fine nodes and control nodes, and creates contextual snapshots at critical nodes for de-optimization. Furthermore, Maglev also performs inlining operations based on feedback information when encountering complex built-ins. Representation selection is prepared for phi and tagging. After the graph construction, all phi nodes are tagged. However, in some situations, if both the input and output values are untagged, Maglev compiler will do unnecessary operations. Therefore, Maglev introduces untagged phi to address this issue. It identifies the types of the inputs and analyzes cases where both the input and output are untagged. Then it converts tagged phi nodes to untagged phi nodes to avoid useless operations. In this stage, Maglev generates some necessary information for register allocating. It removes dead nodes, generates register constraints between inputs and outputs, finds the maximum number of parameters for function calls, and collects information about node uses for evaluating the lifetime of SSA nodes. In this stage, Maglev traverses all nodes in the graph and makes allocation. The allocation is based on linear scan algorithm. The first step is to calculate post-domain calls, which are points that break the assumption of linear scanning. Next, it allocates registers and stack slots, utilizing a cache for efficient allocation. It also merges for register recycling. The code generation phase is based on function templates. It traverses the node graph, emitting deferred code and creating return points for the optimization. If the input breaks the assumption of Maglev compiler, it will jump to the corresponding de-optimization label and falls back to the runtime to execute the bytecode. In Turbofan, due to the presence of the type system, the frame state needs to store a significant amount of information, such as the context and the local variables, while in Maglev, the node system is designed to be simpler, and the frame state only stores key value pairs of registers and nodes. Comparing Maglev with Turbofan, Turbofan has a clear distinction between high-level and low-level nodes, while Maglev does not. As far as the optimization phase, both of them perform inlining. However, Maglev tries to mutate nodes, while Turbofan reduces nodes from high level to low level. During the de-optimization, they have similar designs by using frame state to store the context, but they store different information. In terms of vulnerability, they expose similar attack surfaces on register allocation, inlining, and de-optimization, and Maglev has unique attack surface on phi and tag phase. Besides, Maglev's de-optimization mechanism differs slightly from Turbofan, and mishandling of leave registers can lead to vulnerabilities. Furthermore, Maglev has special optimization of certain syntax structures like exception handling and loops, which Turbofan does not. In this chapter, we will talk about how to conduct vulnerability research on Maglev. After borrowing the experience from Turbofan, we figured out that there are 3 useful methods for bug hunting. They are crash-based fuzzers like Fuzzly and DIE, and differential fuzzers like FuzzJIT and JIT Picker. Also, the source code audit, and we could have some useful tools like CodeQL to help with that. Crash-based fuzzing is our primary method for vulnerability discovery. We enabled fuzzing tests for Maglev, added special function templates. Also, we built the fuzzer under ARM and ARM 1640 architectures based on V8 simulator. The fuzzer found multiple security bugs. As for differential fuzzer, we carried out secondary development of JIT Picker, which is an open source project. After 4 days, we got about 3 bugs. However, after analysis, we found that these bugs are not security related. This is because Maglev compiler does not have a type system, which prevents the calculation errors into mismatch in type system like Turbofan. We also wrote some QL queries for typical bug patterns. For example, if the source code allows running user-defined JS code in promise callbacks, there might be a side effect problem. Additionally, we summarized the root cause of issues we have found in the before, and as a result, we discovered a new bug, which we have reported to Google. The following picture shows that the timeline of our research. Google started developing Maglev compiler in February 2022. On March 16, we adopted Maglev compiler in the fuzzer, but due to some mistakes, we did not really put it into work until September. The class fuzzer introduced support for Maglev. After 3 days, we discovered the first RCE vulnerabilities, and by June 2023, Chrome officially introduced Maglev compiler in their release blog. The debugger is very helpful in bug analysis. Turbofan's Turbolizer converts the optimized node into a graphical interface, so we can debug it by tracking the change in the nodes at each stage. Maglev also implements a tracking system which outputs nodes and basic blocks to the terminal. Each node contains its liveness range and register allocation information. You can also track the representation selecting of input and output during file untagging. Okay, welcome to my partner Bohan Liu to continue with the second part. Thank you.
Okay. Thanks my partner for sharing the part 1, which introduced how we understand the Maglev and how to find bugs in it. I'm Bohan Liu from Tencent Security Xuanwu Lab. Let's continue the part 2. We will talk some interesting cases in Maglev found by the methodology mentioned before. In the following section, I will analyze some typical bugs that I found during different compiling stages in Maglev to show the attack surfaces in it. The first stage is graph building. It's mainly the conversion from bytecodes to errors. There are some aligning operations in it. This is one of the most problematic stages for other JIT compilers. Then comes the representation selecting stage, which mainly involves the type conversion of each node. It's a Unicode attack surface in Maglev, and register allocation mainly does memory allocation and register scheduling of nodes. There has also been problems in other JIT compilers. Finally, there is the optimization, which includes conversion between different levels of optimizers. It's also a more common but less concerned attack surface. In this talk, I will mainly introduce the bugs in graph building, register allocation, and the optimization. Okay, let's begin. First, let's come to the graph building stage. This stage mainly does 3 things: create basic block, add nodes to basic block, reduce some complex built-in call. The third point is most prone to problems. So, as a developer, how to reduce costs? Generally speaking, the JIT compiler usually generates optimized code based on the object type in the feedback. It usually refers to the fast path in the built-in exploited by an optimized executor. If not met, they optimize it. So how to find bugs? We can carefully compare the code in the optimization stage in Maglev with the code in built-in, including checks and other implementation details to find out the differences. According to this idea, we can take a look at this bug. It appears when optimizing a string.prototype.charCodeAt. This function returns the character at the index position as a number. The code on the left is the implementation of runtime function in Ignition compiler. It covers the index controlled by user into an unsigned integer and compares it with the length of a string. The code on the right is an optimization code in Maglev. You can see that it uses checked inter32 condition IR to compare index with length using a keyless mode. So what does the IR generate? When generating machine code for this IR, the keyless mode is used to adapt the logic to the optimize when the condition are not met. But the final code here, you can see, is compare and jump greater equal. This code is signed comparison according to the manual here. This is different from the built-ins. So when the index is a negative number, the code will not be de-optimized and directly return the value according to the number, resulting in a forward out-of-bounds read 1 byte. We can see this here. It's why the POC crashes. But is this just out-of-bounds read 1 byte? According to our understanding of V8 heap, this string will be allocated in old space during the compiling phase. Other objects will be allocated in new space when runtime. And this kind of object address is just before old space. So when continuously read or search via a same string, like this here, we just use a stable offset, and we can also search the special flag. We get a powerful primitive address of object. Next, we enter the register allocation state, which is mainly related to some registers and memory allocation. In Maglev, each node will be allocated a stack slot for storage. In different basic blocks, registers will be used to cache the values of those nodes, used to speed up a size. At this stage, there may be conflicts between read and write size to registers. For example, issue 1296876 is in left off WebAssembly compilers. Register allocations collision causes the value to be modified during use and leads to type confusion. So, are there any register allocation collision cases in Maglev? Let's look at this issue. This is a standard fuzz POC pattern. It seems to be in a constant loop, which may lead to further optimization. This bug seems to be related to the loop structure. As we mentioned before, special handling leads to special bug. We know that Maglev is already in optimized state, but it's not the final state. So when there are enough loops, it will still be optimized in Turbofan. A typed or stack replacement is generated in the loop structure. After the looping enough times, This code will determine how to further optimize. First, it will try to directly replace the cached Turbofan code. Otherwise, it will try to build Turbofan code and de-optimize for further processing. There is an interesting thing which has been marked in red here. Sparkplug compiler has another name, baseline. So the code of Sparkplug compiler is reused during processing here in this code. It applies for a scratch register to save the code object, which mainly a register for transition. So what is the scratch register in Sparkplug? It preserves x14, x15, and x19 for extra registers. It uses them in order for saving time. This seems an exception. So when calling a query script, it will return x14 first. But is the exception universal for in Maglev? It seems not. By tracing the Maglev's register allocation, we can get the x14 should be alive when the optimization, since it's storing the value of variable 257 here. So what's the value of variable 257? By tracing the data flow, we can find that the location here should be a context value from here to here, and this, the context value. We found that the location here, and then it will be set into frame state. So when the optimization happened, a type confusion occurs. We should get a context rather than a small integer here. The bug in the same stage also be issue 1368046. It's a type confusion bug caused by another register allocation collision. We can see that there are more bugs in register allocation than same stage in other compilers. This might be more register scheduling in this stage. The next part is bugs in the optimization. The optimization means that when it's found that the optimized code is not enough to support the current input or state, it will jump to the non-optimized state to continue execution. The process is storing the context snapshot at every de-optimization point and materializing the JavaScript object according to frame state using the snapshot. Finally, jumping to the bytecode position when with unoptimized states. In Turbofan, this is a point that receives less attention, but there still are some interesting type confusion bugs here. So, any difference between the optimization issue in Turbofan and Maglev? So, let's look at this issue. It's also a correct sample found by Fuzzing, which lead to an out-of-bounds write caused by type confusion. We can see that here. In the first loop, the input parameter is always object 4. So it's the target of Maglev optimization. In the second part here, when the JIT code finds that the input is a small integer 1 instead of object 4, it will bail out to ignition. So what kind of error will de-optimize? This is mainly reflected in its properties. When eager de-opt or lazy de-opt exists in its error properties here and here, it means that this node may lead to de-optimize. Eager means do it here immediately. Lazy means do it at nice check. After analysis, we located the bug in the error check maps with migration. Let's take a look at what the error do? First, it is saving all registers according to the register snapshot of node before an auto call at 1. And then it calls runtime function try migrate instance for checking at 2. And it checks runtime status to determine whether to deoptimize. If deoptimized, it recovers ignition context according to frame state and continue executing in ignition. We know that the information used during register saving and recovery is different. For register saving, Maglev's own analysis results, known as live registers, are used, while the recovery uses the analysis results of bad code analysis frame state. Will the difference here cause problems? The result is positive. For live registers, it represents the registers that will still be used after the node ends, and frame state represents the register status during the operation of this node. For example, the R8 in this picture represents the map need to be checked as the parameter of last IR. This node is no longer used after check maps with migration and be needed when building out to ignition. Therefore, the register is not saved at 1. Here, we can see the RDX is not saved. So after a side effect occurs when the built-in function is called at 2, the value of R8 is overwritten by 3, before 3. So during the optimization processing, the lifetime analyzed by the two analyzers are different, resulting in a serious type confusion. The bug pattern is below. First is that we need an IR which has eager deoptim property, and is need an outer call may cause a side effect when generating code. The third one is saving registers using node snapshot rather than eager info before the call. And if there is a lifetime differ between nodes, it will lead to a type confusion. When we translated those node conditions into CodeQL, we found there are some similar errors in Maglev. What's more, we found another interesting error that is checked object to index. It fits the first 3 conditions, so I submitted this as a potential type confusion bug. And V8 team think my guess might be right at the first time. I was so happy to hear it at that time. But happy time doesn't last long, unfortunately. They think in this situation, it's difficult for lifetime differ to exist. We can't eliminate the following check interstate2 condition node which return the node lifetime, but is in need of security risk for further development. Finally, V8 team killed this pattern by refactoring all the related code. We can get from this case, the optimization bugs in Maglev may related to lifetime issue rather than the typer issue in Turbofan. The next section, I will tell a story about an interesting RCE trip in Maglev. This story happened in September 2022. I deployed my father with a Maglev template to server and went on vacation. Starting from the next day, I found my email inbox flooded with reminders of crash samples. And when I returned from vacation, I found hundreds of different crash samples. First, I selected a sample with the best condition to reproduce. Luckily, it still exists at the latest commit. We can guess that It's also a bug in handling with a track structure here. At that time, I know little about Maglev, so I chose to start analyzing from the bad code that I could understand based on my Turbofan research. And finally, I found that the problem was like this. First, in different code blocks, it will create a context object like this here. For example, a new function context will be created at the beginning of function v1. And similarly, there are try and catch contexts at the beginning of each blocks, here and here. Let's call them context A, B, C, respectively. When executing at different code locations, the context will be switched, but a problem occurs when ending the cache here. It is still context C instead of context A. Therefore, an OB write occurred during the following error. The root cause of this bug is confusion between different contexts. Fortunately, context is not a concept introduced by Maglev, but a common concept in JavaScript. It's a variable length object mainly used to store local variables in code blocks. Context A has 3 local variables, v3, v8, v9. While context C has only 1, the result of v3 index of the error. Therefore, with the error in context conversion, offset will be used to write a new value to the short context, resulting in this OB write. When getting such initial conditions, I was thinking how to make the OB write more controllable. Since the length of the context can be changed, I can define new variables to make the writing position more flexible. At one here, I defined so much variables. I also allocate a victim array at runtime to put it after the context at 2, and store them in global variables to make them easier to get. At 3, using OB-write, we modified the length of victim array. Finally, we got a corrupted array and with modified length, which can be used to make more powerful primitives, such as address of, arbitrary read and read. By passing the mitigations such as WebAssembly code area, non-readable, and V8 heap sandbox, finally, I achieved render RCE for this bug in Chrome 107 developers version. It took about 2 days from vulnerability analysis to exploitation. This is a demo. Okay, we check the version. And it's a calculator. But fortunately, the bug was eventually fixed by the time I finished the exploit. It's also easy to understand. After all, it triggered probably hundreds of different crashes in my father. I think it does the same in ClassFuzz Google itself. But this also stimulated my interest in Maglev research, which led to this talk eventually. Let's come to the last section, conclusions and takeaways. In this topic, we summarized the design principles and features in Maglev and analyzed Unicode and common attack surfaces. Besides, we explored the bug hunting method for Maglev. During bug hunting, we found many security issues and finally submitted 7 high-risk bugs of them. We also used one of them to achieve render RCE in Chrome based on our prior knowledge from Turbofan research. I also got the top 20 of Chrome VRP researchers reward this year, which is largely due to this research. When we started this research, Maglev was still in its infancy, however. Through the above research, we believe that Maglev is complex enough. So there are many situations that developers do not accept, and it may become the vulnerable target like Turbofan. We also believe that Maglev's performance and security will continue to improve, and it will play an important role in improving Chrome performance in future. Okay, I would like to thank the following people at the end of this talk. Thanks to Ticket's support and Mulian's help in Fuzzing when he worked at Tencent Security Xuanwu Lab. I also want to thank Samuel and his Fuzzly. It helps a lot when finding bugs, and also VA team for quickly and professionally fixing. In addition, thanks Amy and the Chrome VRP team's work in bug processing. In addition, due to the limited time, some content about more bugs is not mentioned in this presentation and will be included in the release version of this slide tonight. That's all of this talk. Thank you for your precious time and attention. The time seems to be out, and if any questions, we can talk outside later, or just DM me at and Wang Zhou at Twitter. Thank you.
Thank you.